Hello to everybody. So the microphone is active. So let us go to a session which is on exercises of conservative fields. And so first of all, let us go for the first exercise, which says establish whether the planar field and here I write down the field and it is F equal to y squared minus x squared I plus x squared y on the unit vector j is conservative. Is conservative, and if so, find a potential. Okay, so so first of all, this is a planar field, okay? And however, you can also generalize the method of the irrotationality. So the first thing one has to understand here when dealing with planar field is the following: one can check irrotationality. Irrotationality, but oh no, it does not accept irrotationality. But since it is planar, z and the derivative with respect to z do not appear, one has that only the z component of the curl survives. So I recall you what is the reason of what I wrote here. In general, you have that the curl of a vector field f, which means nabla vector f, is what? So it has a first component, which is dy f3, the third component, minus dz f2. This is the first component of the curl. The second is dz f1 minus dx f3. This is the j component plus, and the last component is dx f2 minus dy f1 z. Now we are in the case of the planar field, so there is no z, and here we have that the derivative with respect to z is always 0 because it does not appear. Moreover, there is no f3. So the only component of the curl is the last one. Okay? And so this is another way of looking at the Green's theorem, because the Green's theorem establishes, okay, we are a bit, I became a bit slower with the system. So, moreover, from Green's theorem, we know that every integral of f along closed and regular and so on, a closed curve is the following. So you have gamma, which is closed, then you have f scalar dr, and this is equal to d, which is equal to dy, dx f2 minus dy f1 dx dy, where d is the region internal to the curve gamma. Okay, so this is what the Green's theorem says. We studied a lot. So as a conclusion, what we have is that if the quantity here dx f2 minus dy f1 is identically equal to 0 on the domain of f, and moreover, remember this strange example of irrotational but non-conservative fields, and moreover, the domain of f is simply connected, then f is conservative. So this from a basic observation, applying the basic theorem on conservativity that we already saw, that now we can see through the light of Green's theorem. We have this criterion. This is an important criterion. If, what is this? No, I want to put another color. So if we have that this quantity, which is the third component of the curl, but at the same time, which is the integrand in Green's formula, is equal to 0 identically on the domain of f, and moreover, the domain of f is so-called simply connected, which means that has no holes. So no holes in the plane, then f is conservative. Okay, this is a very nice and very important thing. And so let us verify it on our example. So we have that f is the field here. Let us copy it. F is this field. So now let me compute Vx f2 minus dy f1. This is dx x squared y minus dy, and here we have y squared minus x squared. This is equal to 2xy minus 2y, and this is different from 0, so f is not conservative. Okay, because simply, since this is different from 0, it is possible to find a region where its integral is not 0. And so the line integral on the contour of this region will be not 0 due to the Green's theorem. Okay, so this is very easy. You find that the curve is not 0, then f is not conservative. You have nothing to add to that. So let us try with another example, and the second example is the same question, which means conservativity, and if so, if the field is conservative, potential for the field. So let us put here another field. The field this time is f equal to y squared minus x cubed y cube I plus 2xy minus 3 over 4 x4 y squared j. Okay, so dx f2 minus dy f1 is equal to what? So dx f2, this is what you have to differentiate with respect to x. So you end up with 2y minus 3x cubed y squared minus, so this is this guy here, this is this guy here, and then we have minus, and now dy f1, which is 2y minus 3x cubed y squared, and this is equal to 0. So f is irrotational, moreover, here we have that f is polynomial. So its domain is all R2. Is the whole set R2, the whole plane. And the whole plane, of course, is simply connected, has no holes. Then, in this case, f is conservative. Okay? And now we have to find a potential. Since it is conservative, it has a potential, and so let us find it. Concerning the potential, remember what is the method. The method is always the same. So pick a point at random. In general, one uses the origin as a starting point, then go to another point xy, for instance here, and then integrate the field going from 0 to xy through some quite easy path, and an easy path can be this one. This is gamma, which is made of two sides. This is gamma 1. This is gamma 2. And then what we have is that gamma, we define it as gamma 1 union gamma 2, and then we define the potential uxy. We know that it exists because we already established that the field is conservative. So u of xy is the integral on gamma of f dot dr. And so f dot dr is equal to the same integrand on the curve gamma 1 plus the same integrand on the curve gamma 2. And so in the curve gamma 1 we can use the parametrization since only x is varying, so we have x1 is equal to t 0 with t in 0x, and gamma 2 is x t with t in 0y. Okay, now we see that in gamma 1 we have r dot, which is 1 0, here r dot is equal to 0 1. So here you have that f has this x component, the only that survives, but this component is equal to 0 on the curve gamma 1, because here we have y equal to 0. If y is equal to 0, this is always equal to 0. This sort of miracle happens quite often with the fields we are giving you for exercises. So it is not a lucky circumstance we met now. It is almost always like that. When we split the path in this way, usually the first step gives you 0. With the fields we are giving you, this is not a law of nature, it's just a law of exercises you find in books, because they are polynomials, so when you have a variable which is 0, the field goes to 0. But okay, this is just a sort of hint. Okay, it is not a theorem. Sometimes it is not 0. We can be so tough and give you a field which is not 0 in a contour like that. Okay, but in this case it is 0. So now we have 0 plus the second. In the second we have that the field here is this guy here. So we have our expression of the field on the curve when we replace to the variable y t. So we have 2xt minus 3 over 4 x4 t squared. So this is 2xt minus 3 over 4. It was x to the third, x to the fourth power t squared. And only this component survives in the scalar product, because we have to make the scalar product of f times r dot dt, and r dot is 0 1. Okay, this nowadays it should be quite understood. If not, stop there, understand it, or write me some comment and so on. So now we just integrate this field. This is the integral from 0 to y, and this is x t squared minus 3 over 4 x4 t cube over 3, because we integrated t square and we get t cube over 3. Of course, this 3 cancels the other one, and now we have to evaluate the integral between 0 and y. So we end up with x y squared minus x fourth y to the cube over 4. Okay, this is our potential, so let us verify that u x y equal to x y squared minus x4 y cubed divided by 4 is truly a potential. So you have the following, that du dx is equal to 2xy minus x3 y3, and this is exactly the first component of the field, and the second du dy is, oh sorry, not 2xy, it is y squared, and here we have 2xy, we have to differentiate it with respect to y, minus 3 over 4 x4 y2, which is f2. So this is truly a potential. Okay, so this is in general how you solve an exercise like that. Of course, exercise like that will be given in the form of a multiple choice test. For example, example can be so given the field, and then we give the field that you already know, f equal to y squared minus x cube y cube y plus 2xy minus 3 over 4 x4 y squared. So, for instance, which one of the following statements is false? And here you have a first, f is irrotational. Then f is conservative. Three, the domain of f is not simply connected. Fourth, the integral of f on every closed regular curve is 0, and the fifth, for instance, it can be u xy is equal to what we found, xy squared minus x4 y cubed over 3 over 4 is a potential of f. Of course, you go also by logic, but however, if you start from the last answer, you verify that it is a potential, so f is surely rotational and f is conservative. This is more delicate, but the domain of f in this case is all R2, so it is simply connected, and so since there is a knot here, 3 is what you have to check. And the fourth is just another definition of conservative. A field is conservative if and only if its line integral along every closed curve is equal to 0. So, bye.